Hello and welcome to episode number 5 of CS350 Online. I'm your host as always, Leslie Ested, and in today's episode we're going to continue our discussion of synchronization, and in particular we're going to look at load, link, and store conditional from a couple different perspectives, and then we're going to start looking at locks that block instead of locks that spin, and possibly we'll also get into some semaphores and condition variables today as well. Just a couple announcements before we really get started. One, if you haven't started assignment 1, please do get started. It's not too bad of an assignment, but please note that we accidentally left some debugging code in it. Our sincerest of apologies. So please make sure you're paying attention to the Piazza post to note the little change that you're going to need to make to assignment 1, question 2. As for assignment 2, it's going to be available soon, hopefully mid to later in this week, more likely, and you'll be able to get started on that shortly as well. And the other thing I wanted to mention is our quizzes. They will be available soon as well. We are going through them and trying to improve the quality of the questions so that there's less confusion when you are actually doing the quizzes. All right, before we get into, of course, our lovely topics, I'd like to talk about the OS of the day. And today's OS is called CTSS, or Compatible Time Sharing System. And this is an operating system that was released in 1961 from MIT. And this ran on the IBM 7094, which you see pictured in the bottom corner. Now, this operating system is actually quite important in the grand history of how did we get to where we are today, because this operating system is the predecessor to an OS known as Multics, which some of you might have heard of. Some, not everyone. And if you've heard of Multics, or even if you haven't, what you might note about it is that Multics is actually the predecessor of Unix. And Unix, of course, is the predecessor of many of the things that are sitting in front of you today. So whether you are using a GNU Linux-based operating system, or whether you are sitting in front of a Mac, you can thank all the way back to CTSS. So what's so interesting about this operating system? So, for one, this is the first operating system that demonstrated that the concept of time sharing was actually feasible. And how they did it was they were able to context switch 4 different users to tape. So they gave the illusion that all 4 people were using the computer at the same time by swapping them out to tape. Now, what do we mean by tape? Well, if you look in this picture down here at these refrigerator size units with the 2 wheels in them, that's actually a tape drive. And that's what they were actually being context switched out to, was these lovely tape drives here. So they've demonstrated that this was feasible. And they also did a whole bunch of other little things that of note. So they had the concept of online file systems and file sharing. So to make things easier for the users, instead of having to, put it on a disk and then hand the disk to somebody else in order to actually get the files off, they had this idea of a shared file system where they could actually send files and access files between each other. And that's a pretty cool feature. So you could share files, so there could be common files, you could have symbolic links, and this actually enabled the community to share data more easily, which is a really good feature. And in some ways, this was early seeds towards cloud-based work, or network drives. Some other interesting things that they had was they had text formatting utilities, and they had one of the first user messaging programs. The ancestor of email was actually one of the applications offered by CTSS. So you could actually send a message and to another user, and if they were on the computer at the same time, they could actually read it right away. So it's kind of like an instant message. And they also had one where you could leave messages behind for people who weren't actually on the computer at that time, so kind of like an email. They also had something called QED, which is the predecessor of Vim, for anyone who's a big fan of Vim. So this is a pretty important OS overall. All right. Where did we leave off then? So if we go back into our lovely synchronization slides, make this full screen here. We left off talking about the importance of having mutual exclusion. And in particular, we noted that when we have I'm scrolling in the right direction. Anytime we have a piece of code where we have a shared variable, and that could be a global variable, that could be a heap variable. But anytime you have a shared variable that could be read and written by multiple threads at the same time, you have what's known as a critical section. So wherever you are accessing that variable is a critical section, because the order of thread execution through that block of code where threads are reading and writing it at the same time really matters. It's critical it behaves properly. What we want is to offer mutual exclusion. That is, we only want one thread able to read or write this at any time. So in order to protect this, we needed some kind of mechanism, a locking door. And we introduced the concept of a basic lock. Let's go here. And in particular, this was our lock implementation here. So our lock itself was just a Boolean, and then we had acquire and release functions to acquire the mutual exclusion, do our bit, and then leave the mutually exclusive area. And if we do this wrong, we end up with something called a race condition. And recall that there are 3 different sources of a race condition, and we've only actually discussed one of them, and that is the one that's our fault for not actually protecting our shared variables. And there are 2 others we'll talk about later. But what a race condition causes is when you run your program, the output depends on the order of thread execution, you have a race condition. And how the race condition presents itself could be incorrect output. It could be runtime errors like segmentation faults or bus errors. And it can even just be a memory leak that happens silently. So there's lots of different ways that race conditions can present themselves. And they are notoriously difficult to find and repair. I think there was a study done by Google a few years ago, maybe 2 years ago. I've kind of lost track of time. What day is it? And Google actually ran some analysis on the Linux kernel to see how many race conditions and deadlocks actually exist in the kernel code. And it was well over 300. So this is something that is open source and people are actively developing, and anyone can go in and look at the code and try to improve it. And there are still hundreds of problems with synchronization in it. So this is very, very tricky to work on. Now, if you're thinking, well, that's because it's Linux. Well, I bet Windows doesn't have any of these things, and I bet Mac OS doesn't have any of these problems. Oh, yes, they do. I promise you they do. Now, one of the problems we ran up against with our spinlock was the fact that in order to get a very efficient way of doing the test and set atomically, that means uninterrupted, we had to make use of the hardware. So for x86, we used the exchange instruction. And for ARM and MIPS, we had to use a pair of instructions, a barrier. So I'd like to just review that briefly. Now, normally I would do a couple different ways today showing you how you might actually think about this, but one of them I'm just going to post to Piazza, and it's a tree approach to thinking about how load, link, and store conditional work. And the other one I will actually do here. So let's open up this horrible program here. It's not going to open on the right screen because it never does. Why would it ever do what I want it to do? Of course, the problem is when you have a dual monitor setup and there's a huge difference in your 2 monitors, it's actually a pain to drag something from the big monitor to the small monitor. All right. There we go. So what we're going to do is we are going to look at load, link, and store conditional. Remember, load linked gets the value at the address right now. And store conditional stores a value at the address, and I want the word is, I want the word if, the value at the address hasn't changed. Since the load length. So if the value at the address has not changed, then store condition will put a new value in and return success. If, however, the value at the address has changed, then store conditional will not be able to store a value at the address and it will return a failure. So that's the high level what's going on. Now let's take a closer look at kind of the code. So let's use, we are going to say that SD is my address. So I'm going to say X is equal to the value at address SD. So what I'm doing right here is this is the load linked instruction. Okay? That's good. Now, the store conditional. So what it's going to do is if X is equal to the value at SD, I'm going to set SD equal to 1 because I want the lock. Now this does not mean I have the lock, as you're about to see, but I want the lock. So the next thing that I'm going to do, still in this branch, is I'm going to set my return value Y equal to success. So at this point, X has the old value of the lock, SD is the address, and we've set the value at SD, better dereference it here, to 1 to say I want the lock, and we've said that store conditional succeeded. Otherwise, if the value in X is not equal to the value at the address SD, then I'm going to set my return value Y to failure. Okay. So that's the first part. So that's the store conditional part. So if the value at X hasn't changed, then store conditional will succeed. If the value at X has changed, then store conditional fails. Now here's where things get interesting. There are different outcomes. So just because you succeeded in setting the value of the lock doesn't actually mean you got the lock. Let me explain. So you actually use a different color here. Let's use, for the sake of fun, red. Yes, for the person on Twitch who's saying, would the value of at SD be dereferenced SD? Yes. We could just use pointer arithmetic. I don't know why I wasn't. Same thing. All right. So, if Y equals success, so after load link and store conditional have executed, if Y is equal to success, there are two possibilities. The first possibility is if X is equal to false. So remember, that's the old value of the variable SD, the old value of the lock. So if the old value of the lock was false, then the lock was available, and since store conditional succeeded, we succeeded to change the value of the lock to 1, which means we actually got the lock. So we will return false, and this is going to cause us to stop spinning and we own the lock. Okay, so that's case 1 for success. Case 2 for success is if X was not equal to false, if X was equal to true. So the lock was already not available. Ugh. This is the weirdest thing. So if the lock was not available, then we are going to return true. Because we just swapped 1 for 1. So we didn't get the lock was not available. If we return true, we keep spinning. And there. No lock. Okay, move out of the way. Move my chair out of the way. Now you can see it there. The final case is if Y equals failure. Now, if Y equals failure, we return true. And we keep spinning. And we don't get a lock. So there you go. Now, some people like to ask me, well, what if the value changed? So, and you knew that the old value of the lock was true. So if the value changed, wouldn't that mean that the lock is now available and therefore you could just take it? But making that assumption is actually a wrong one to make. That's assuming. So first off, stored conditional doesn't actually care what the value of the lock is, because it's just looking at the value in a register, or a value in memory, and it doesn't care what the value is. It's just comparing the old value to the new value. It doesn't care what the value is. So it's not going to check whether it's false or true. This here is load, link, and store conditional up here. But everything below this yellow line is actually the wrapper code for calling the load, link, and store conditional. So we only check whether the lock is true or false in the wrapper code. The actual assembly instructions don't even look at what it is. And then you're like, but if it was true and it changed, it could only change to false, therefore we could get the lock. And it's like, well, how do you know? Because the values in memory for stored conditional, you're thinking that it's using 1 bit or 1 byte to actually store true or false, but it's not. It's actually for load, link, and store conditional, we're actually using integers. So it might have been 1, and now it might be 356,000. There's nothing, and load, link, and store conditional don't care. So we can't make the assumption that it was true, and now it is not true. That means it must be false. So you can't make that assumption. All right. Now on Piazza, let's open a new window here. I will open up Piazza. For those of you who haven't seen this thread, and I do hope that you have seen it, there's this extra lecture content, guides, and problems. And in here, you will see we have a bunch of guides. We've got this load, link, store conditional for MIPS, and that's actually this lovely tree here that will break it down into what are all of the different paths that you can take. So starting with the load linked, and then we've got the store conditional, and then the 4 possible outcomes. And oh goodness, there is actually a bug here because this one should be, oh no, there's no bug. I'm being silly. There's no problems with this. Anyways, this tree here will actually show you a different way of thinking about how do we actually go through this load, link, and store conditional. And just for the record, there's all kinds of other things in here. We've got, if you don't remember how to do pointers, there's this silly thing called Pointers, a bedtime story. We've got information about context switches, a guide for making locks, condition variables, and all those other lovely things. So make sure you do check this thread out. All right, so then, I don't want to recap anymore. let's go back to our slides. Now that I feel like we have a pretty good understanding of what this load, link, and store conditional are doing, in our last episode, we did talk about spinlocks as being the basic implementation of this. And a spinlock is a lock that spins. And that means that if you try to acquire the lock and the lock is not available, you are going to sit there in a loop and repeatedly ask, hey, can I have it? Can I have it? Can I have it? Can I have it? Until you actually get it. Now, if you actually look at lock implementations, spinlock implementations, you will note that spinning doesn't actually really happen. And the reason for that is we've set the CPU to be the owner of the spinlock. Now, normally you think of the owner as being the thread that is using this shared variable right now. But the reason why we are using a CPU as an owner instead is because when you acquire a spinlock, you disable interrupts on that CPU, which means that that CPU cannot have preemption happen on it, which means that on that CPU, no other thread will run, and therefore, effectively, the spinlock is owned by a CPU. That doesn't prevent, and that means there will be no spinning happening on that CPU. That doesn't prevent spinning happening on other CPUs, though. It really comes down to an architectural decision. If you disable interrupts, are you disabling them across the system, or are you just disabling them on that particular core? Again, architectural implementation details. But in our case, it means on this CPU, these are disabled. Now, there are pros and cons to doing this. Pro, no spinning. Con, the longer you own the spinlock for, the more interrupts are going to get ignored. And what happens to ignored interrupts? Now, some architectures actually have the ability to queue interrupts at the CPU. But my understanding is those queues actually tend to be quite short, only like 1 or 2 long. So anything beyond that is going to just get dropped or ignored, which usually means that the devices that are throwing the interrupt will actually repeatedly throw the interrupt until you actually deal with it, the problem. So it's a bit of a pain, but that's how it tends to be done. So the point I'm trying to make is spinlocks are really good for if you need to protect a really tiny critical section. But if you need to do something more complicated, you really shouldn't be using a spinlock because you're disabling interrupts and they could get dropped or lost, or you could otherwise just cause problems. So spinlocks are for short things. And I believe I showed you this inline assembly here yesterday. Well, by yesterday, I mean like last week. Again, we do not expect that you understand this inline assembly. We just want to show it to you because it's good to see. What we really want, though, is since I can't use a spinlock for anything big, what if I want to protect a critical section of, say, my ray tracer? Please don't do that. That's a really bad idea to implement them that way. But let's say we implemented a ray tracer poorly. That's something that effectively traces the path of light as it goes from your eye into the scene to figure out what color is that pixel going to be. But let's say that for some reason I needed to protect access to my eye, so I can only send one ray at a time. This job of ray tracing is a really expensive job. So a spinlock to protect my eye would actually be a really bad idea. So I need a lock because it's going to disable interrupts, or I'm going to have spinning for long periods of time. What I want is a lock that blocks. And the idea behind a lock that blocks is you show up at the DC bathroom, you see that the door is shut. So instead of sitting there and knocking on the door, hey, you done? Instead, you're going to fall asleep on the floor. Now, obviously, I don't recommend you do that, but let's pretend the bathroom was actually clean. So you fall asleep on the floor. The reason why that's a good thing is because if you are asleep, you are not ready, you are not running, you are blocked, which means that other threads will get an opportunity to run. You are not wasting resources repeatedly checking whether the door is open. The idea then is when the person who is in the bathroom stall leaves, they open the door, and when they open the door, they're going to wake you up. And, you will have an opportunity to acquire the bathroom. So that's a lock that blocks. And these are not implemented in OS 161 for you. Now, they used to be a part of assignment 1 where you would implement locks and you would implement condition variables and then you would solve a problem with them. But we decided that we'd like you to get a bit of experience with threads and using these kinds of primitives before you actually try to implement them. So assignment 1 now is done in P threads, and on assignment 2, the very first thing that you're going to do is actually implement locks and condition variables. And don't worry about it. One of the reasons why we were okay pushing these to assignment 2 is because for locks, we're going to give you the pseudocode, and the implementation you can almost copy verbatim from semaphores, which are implemented for you. But the condition variable code as well is fairly straightforward. So we're going to walk you through the creation of locks and condition variables. But before we look at the lock implementation, we need to talk about the API. So it's very similar to spinlock, but it's, I want to say, higher level, friendlier functions. So we've got create and destroy. We have an acquire and release function, and then we have this other function called do I hold. And lock do I hold is used to check whether at the point you call this function, do you own the lock? And the idea here is if you don't own the lock, because you just asked if you own the lock, you're not going to own the lock when you return from this, so that won't have changed. And if you did own the lock, then since you were just calling the lock do I hold function, that's not going to change either. That comes into when you're implementing this. But now we have to talk about blocking. So what does that even mean? So we need the ability to have a thread wait for something else. Obviously, we want to be able to wait for a lock to become available. There are other things that we might wait for. We might be waiting for input from a keyboard or some kind of device. So for example, there will be OneNote is running on my laptop right now, and OneNote is actually waiting for input from either my keyboard, my mouse, or this tablet pen. And it needs to wait until that happens. Another time where you might actually see this need for waiting is when you're waiting for a slow device, like a printer to print. You can't print another print job while one is running. We need mutual exclusion on the printer because it would be really weird if, somebody else's work started printing out in the middle of yours. This actually used to kind of happen in MC. So back in the day on the 3rd floor of MC, there was a print room. And when you wanted to print like your work term report, because we actually used to have to print them and hand them in and bind them and all that. I had to do work term reports. Didn't have to do any of that PD nonsense, though. Did not exist. But in order to go print your work term report, you'd walk into this room, you'd swipe your walk card on one of the printers, and your document would print out. And if somebody came along and swapped their walk card while your document was printing, you obviously don't want their document to print out in the middle of yours. So we need a way to block or wait for the printer to finish before we send the next job to it. Another place where we need waits are, let's say you wanted to actually enforce a thread to sleep for a period of time. Now, you may not see a use for this, but this is actually something I use in my own code. So I have a little graphics code. It tends to be incredibly computationally intensive. Not so many context switches. Certainly there's no voluntary thread yields, and there doesn't tend to be a lot of blocking either. It tends to be a lot of raw computation. And if you're trying to do something like that on a laptop, your laptop might overheat, and I have this problem a fair bit. I have actually had a laptop catch on fire. Not my recent one of my older laptops. I actually had flames coming out of the keyboard. But if you want to keep the temperature down, one of the things that you can do is enforce computation breaks. So what I used to do in my code on my older machines that weren't so good at heat dissipation was actually put periodic breaks in. So maybe every 10,000 iterations, I would have a sleep for 2 minutes. And yeah, that's going to impact my performance, but it also means my computer's probably not going to die because that computational intensive program is actually going to take a break. And none of the other programs I tend to have would be computational intensive. So there's lots of different reasons why you might want to wait. When you are waiting, remember you are not running on the CPU and nor are you in the ready pool because you are not ready to run. You are waiting for something. And where threads go to wait is what's known as a wait channel or a wait queue. Now, how do you implement this? Do you have one master pool of all of the threads that are waiting? You could, and I'm not saying that nobody's done it this way, but here's the problem. Some threads are going to be waiting for you to push the any key. Some threads are going to be waiting for 2 minutes to have elapsed. Some threads are going to be waiting on locks, and some threads are going to be waiting on blocks. And some threads are going to be waiting on this and that and the other thing. So you've got all these threads waiting in this pool. And when one of those events actually happens, let's say somebody pushes the any key, how do I identify which of the waiting threads I actually need to wake up and move from the blocked queue to the ready queue? Well, I'd have to go and ask every single thread that's waiting, hey, what are you waiting for? That's going to be really expensive. We kind of want this to be fast. So what we actually do is instead of having one master pool, we actually have wait queue for each and every single thing you can wait on. So if there is a thread, if threads are going to wait for 2 minutes to elapse, we will create a wait channel for the threads that are waiting for 2 minutes to have elapsed to sit on. If we are waiting for a particular lock, then we are going to have a wait channel for that particular lock, and the threads that are waiting on that lock will wait in that wait channel. And that way, when I know the lock is available, I will go to that particular wait channel and wake a thread there because I know that all of the threads on that wait channel are waiting for the exact same thing. So we tend to have one wait channel per resource or thing we are waiting on. Wait channels are already implemented for you in OS 161. They are called WChan. There is a small API. You have sleep, wake all, wake one, and lock. Now, most of these functions are atomic. So wake all and wake one are atomic. That is, they are not interruptible. But sleep is complicated. All right. So we have a question on Twitch. How specific are the wait channels? Will a thread waiting for 2 minutes to elapse be in a different wait channel than one waiting for 3 minutes to elapse? Yeah. So generally what would happen, I mean, if I were to implement this in my operating system, keep in mind every OS is going to implement this completely differently. But if I were to implement this in my OS, I would actually have, when you call sleep, which is a system call, and we'll talk more about that another day, when I call sleep, I would actually be creating a specific wait channel for a thread waiting for 2 minutes, and I would put my thread onto it. And when the 2 minute timer elapses, and the kernel would be handling the countdown, when that 2 minutes has elapsed, the kernel would be responsible for waking the thread on that wait channel. And since a 3 minute wait is a different amount of time to wait, and I would have a different wait channel for it, because they're two very different things. Because I don't want to have to go to the wait channel and say, oh, which ones of you were waiting for 2 minutes? When did you go to sleep? And has 2 minutes elapsed? I want to know that this thread waited for 2 minutes, and when I wake it up, it's the only one I want to look at. I don't want to check 30 other threads. So yeah, generally speaking, wait channels are highly specific. Highly specific. All right. Now, I said sleep is kind of funny. So sleep, because of what we're going to see with the implementation of a lock, sleep cannot lock the wait channel before it puts the thread onto it. So we have to have the lock operation separate and external to sleep. But sleep will unlock the wait channel when it is done. Now, why do you need to lock and unlock these wait channels anyways? Because the wait channel is a shared resource. It may be accessed by multiple threads because there may be multiple threads waiting on that shared resource. So we do need protections for that shared queue, because that's how we implement wait channels, is a queue, a FIFO queue usually. All right. So just to remind you of the states of the thread you've got ready, these are threads that could execute immediately but aren't. They get dispatched to running. If you are blocked, you will go from running to blocked, and you will sit on a wait channel, and it is another running thread that will wake you up. All right, we have another question on Twitch. How are waking conditions represented in the code? Some custom structure. No, there is no custom structure to represent the conditions for waking. Effectively, what's going to happen is for something like the sleep, let's say you create a wait channel for a thread to wait for 2 minutes. What you would end up doing is you already have the clock device sending interrupts every so many milliseconds to implement preemption. And the idea is upon each of those preemptions, for the timer interrupt, not the preemptions, for each timer interrupt after, 5 milliseconds has elapsed, the clock's device driver handler is going to have to go through and say, okay, and there may be an array of wait channels for things that are sleeping. And it may have to ask, is any thread waiting? So, to be woken. So, that's actually a really bad example there. But effectively, you're going to have code that is another thread is responsible for waking you up. So in the case of sleep, that's actually going to be the kernel of the operating system is going to be responsible for noting that you are asleep. You are asleep for a period of time. And okay, now we need to start checking on timer interrupts whether any of those clocks, those sleeps have expired. And one of the ways that they could do that for sleeps in particular, they might use a structure for that to say, okay, this is a sleep thread. And I would have a structure that has okay, here's the time, here's the start time, here's how long I want to sleep for, here's the wait channel. So that when the timer interrupts, I can check all the array of sleep structures and do that. But if you look at how wait channels are used in things like locks, in lock release, because you are the thread that is releasing the lock, it is your responsibility on exit to wake a thread. So the kernel handles some of this, and it may be done via structures, but there is no specific wait channel structure to keep track of the condition. A lot of times it's actually another thread that's keeping track of the condition and calling wake on behalf of the threads that are asleep. So hopefully that kind of gives you an idea. It's really specific to the use case. For example, in the old assignment one, you could have technically used a wait channel straight up, and then your code could have manually checked the condition. So, all right, we're not going to move on to semaphores yet, because what I'd like to do now is actually implement a lock. And I'm sitting here, I'm debating, do I want to use OneNote or do I want to use VI? I think I'm going to go with VI. Because why not? VI is prettier. And you can probably read it better. So hopefully for those of you who are watching, the font size is big enough for you. So let's say I wanted to implement a lock. So there's a couple things we know about the implementation of a lock. One of those things is that I know that we're going to need to test and set something. And when I'm testing and setting the lock variable, it's got to be atomic. Now, how I achieved that in the spinlock was by using assembly code. I don't want to use assembly code in my lock. I want my lock to be just written in C or just written in C++. So I'm going to use higher level abilities. So maybe to protect the atomic test and set of a lock that blocks, maybe I'll use a spin lock. So I'm going to create some kind of lock structure. And I'm not going to give you all of the details here. But we probably need a spin lock for providing atomicity without going down to assembly. And then in addition to the spin lock, another thing that I probably need is, well, I need a place to store all of the threads that are waiting for this lock. So we probably also need a wait channel. Now, because locks that block aren't spinning, we don't need to disable interrupts. So a thread is going to have an owner, or a lock is going to have an owner, and that owner should be a thread. We also need a held variable to indicate whether the lock is owned or not. So you might want to have some things in here. I'm going to let you decide how you implement the rest of this. Okay. Now let's look at the lock acquire function. It's actually quite hard to type when you have a microphone sitting right in front of your keyboard. Okay, let's see if I can get that in there without changing everything. Okay. So we've got lock acquire, and we're going to have, a lock passed in. What happens inside the acquire function? Okay. Well, I'm going to give you a little implementation here. And then we're going to discuss whether it works or not. This is all pseudocode, keep in mind. And so I'm going to be kind of lazy in typing things. Now, one of the things you'll notice is that when I use synchronization primitives to protect a critical section, whether it's for mutual exclusion or something else, you'll notice I actually indent. So I have a spin lock that I'm acquiring here. And you'll notice I'm going to have all of the code that's protected by the spin lock indented. This is not required. This is just a stylistic preference that I have. And the reason why I do it is because it kind of makes it obvious as to what code belongs to the critical section protected by that spin lock. It's up to you whether you do it or not. It doesn't matter. We do not mark style in this course. Want to know something else? We don't run Valgrind in this course. So if you're panicking like, oh my gosh, there's 4 bytes that aren't being freed, we're not running Valgrind. We're especially not running Valgrind in OS 161 because we don't have a Valgrind for OS 161. So don't panic. All right. Anyways, this is just a stylistic thing I do, is I like to indent things that are inside of a critical section. So inside of this critical section, I'm going to have a while loop while my lock is held. I am going to... I'm not going to use brackets. I'm going to be lazy today. So I am going to release the spin lock. I'm going to go to sleep. And if you're like, why do you put so many spaces around your brackets? Because I like it that way. Because it makes my code easier to read. All right, so after that, we've gone to sleep. We're then going to reacquire the spin lock. Now we are done with the while loop. I'm going to take the lock. It's good spelling. I'll explain all of these lines here in a minute. Okay, so there you have it, my initial implementation of a lock acquire function. And the question is, does this work? And if you're sitting there madly typing this down like, oh my gosh, here's the answer, this doesn't work. This is missing a few things. So let's start at the top and kind of walk through what's going on here. So I needed to atomically test and set the lock's variable value, and that's the held field. So I'm going to use my spin lock to protect the test and set of the held field. So I acquire the spin lock and then I check if the lock is available. If it isn't, I release the spin lock. Why do I release the spin lock here? Well, I'm releasing the spin lock because I know at this point that the lock is owned and therefore I can't set it. So I test, but I can't set, so I release the spin lock. And then I'm going to go to sleep. If I went to sleep owning this spin lock, we'd have a big problem because then the thread that owns the lock couldn't even release it. So it would actually cause a pretty bad deadlock. So you should never fall asleep while you own a resource. That is really, really bad. So we have to release the spin lock before we fall asleep. Once I wake back up again, you might be thinking, well, I woke up because somebody said the lock was available. Well, that should mean I should just be able to take the lock. You can't, though. Because when you wake up, when somebody calls W-Chan wake 1 or wake all, that doesn't cause you to run immediately. That causes you to go from blocked to ready. And then at some point, the scheduler will schedule you to run, which means that other threads could go in front of you and could steal the lock out from underneath of you. So when you wake back up, you have to reacquire the spin lock and perform the test again. If you find that the lock is not owned, then you can set the owner and the held status of the lock and release the spin lock. Why is this wrong? Well, at the top of the code, what happens if somebody passes in a lock that's null? What happens if somebody passes in a lock that you already own? If you already own the lock, then when you try to acquire the lock, you're going to fail, which puts you to sleep. Since you're asleep, you can never release the lock, which means, wait a minute, nobody can wake you up. Now, why can nobody wake you up? Well, let's go back to the bathroom example again. If you are in a bathroom stall, do you want people to be able to reach their hand over or under the door and unlock it on you? Obviously not, which means locks can only be released by their owners. So if you fall asleep on a lock that you own, since you're the only person that can release it and you're asleep forever. So we might want to have some assertions in here. I'm going to let you decide what they are. Assertions about null and assertions about ownership. And if you're making some assertions about ownership, you should be using that lock do I hold function. So you're going to need to implement that function on your own. Okay, are there any other mistakes? Yes, there is another big mistake with this code. And the other big mistake with this code is the fact that the W-Chan sleep, remember I said it can't lock the wait channel? It doesn't lock the wait channel. So where do we lock the wait channel? Now this is going to be confusing. We lock the wait channel before we release that spin lock. And it has to be in this position because this is what is going to happen. So first off, sleep unlocks the wait channel, so you don't need to worry about that. It's just if you don't lock the wait channel while you have mutual exclusion on the lock, what would end up happening is you see that the lock is taken. So you release the spin lock and then you enter so you release the spin lock and then there's a context switch. The context switch goes to the thread that owns the lock, and the thread that owns the lock is like, okay, I acquired the spin lock. I'm going to release the lock, and then I'm going to wake a thread on the wait channel, and then I finish with the spin lock. So the lock is now available, but when we context switch back to the other thread that was trying to fall asleep on it, now the lock is available and it ends up calling W-Chan sleep and falling asleep on a lock that's available. So in order to prevent that situation from happening where a thread is trying to fall asleep on the lock at the same time it's being released, we have to lock the wait channel while in the critical section, the mutual exclusion, for the actual lock itself, the lock's data. So we're going to lock the wait channel, then we release the spin lock, and this is going to prevent the thread that is releasing the lock from calling W-chan wake until you've fallen asleep. So that will prevent you from falling asleep on a resource that's available. And the rest of this implementation, by the way, is correct. And we actually have the pseudocode for this, by the way, posted on Piazza already, so you can already get started. Now, what about release? So release is actually fairly straightforward. Again, we're going to take a pointer to the lock structure. We need to, because we are accessing the shared variables of the lock, we need to use our have mutual exclusion, so we're going to use that. And it has to be the same one that we used in acquire. So we're going to use the spin lock. Then what am I going to do? I'm going to set lock held to 0. So I've released the lock. I'm going to set the owner to null because nobody owns the lock. Then I need to wake somebody. So I'm going to call wake 1. And then I'm done with the lock, so I release the spin lock. Please excuse the spelling mistakes. Now, why have I chosen to call wake 1 as opposed to wake all? Wake 1 takes one thread and moves it to ready. Wake all takes all of the threads and moves them to ready. Why wake 1? Well, because a lock can only be owned by one thread. So if I wake everybody, if there are 1,000 threads waiting on a lock, and I wake them all up, then they all go into the ready queue, and then when they run, 999 of them are going to go back to sleep. What a waste of computation time. Now we need something else here that's missing. And what's missing here is I actually need to test for ownership. Assertions about null and ownership need to go right there. Because in lock acquire, you don't want to be the owner of the lock. But in lock release, you must be the owner of the lock because you don't want somebody reaching their hand under the door and unlocking it on you. So there is some pseudocode for you to play with for implementing locks for assignment 2. Now, if you're looking for additional help, because again, this is pseudocode, you will note that we recommend you look at the semaphore implementation in OS 161. And the reason why we recommend that you do that is because semaphores their implementation is almost identical to a lock's. So that's pretty cool. The other thing is that, and I mean, when it comes to especially like lock create and lock destroy, like let me tell you how I implemented. I copied sem create and sem destroy into lock create and lock destroy, and I made some tiny modifications. And then for lock acquire, I did the same with the semaphore code. I grabbed the semaphore acquire function, which by the way is called P. We'll find out why in a minute. And I copied its code into lock create or lock acquire, and then I made the modifications necessary. So this is really simple to implement. You have the code. You just need to copy and paste it and make a few modifications. We don't, by the way, want to do anything with interrupts in a lock. All right. So there's our implementation of a lock. And now I want to talk about semaphores. I don't know where in the world you're all sitting at right now. I'm here in Waterloo. It's snowing pretty hard. Okay, so we have a question on Twitch, which is how does the W-chan lock with its own internal spin lock? Yes, so the W-chan implementation actually has its own little locking mechanism, so you don't need to worry about what it is or how it is implemented. You just need to call lock before you sleep. That's all you need to make sure. And the functions wake 1 and wake all are actually atomic already, so you don't even need to worry about it. All right. So I want to talk about another synchronization program. So I might have led you to believe that the only kind of synchronization between threads that you could ever want to do is mutual exclusion. So I want to make sure that I am the only thread accessing this shared variable at this point in time. It's not true though, because sometimes we want to do more complicated interactions between threads. Maybe we could actually let 5 people into the critical section. I want you to imagine yourself perhaps back at school. So let's suppose that this class was actually running an MC and we had to go into MC 2038. Well, that room has 90 chairs in it. There are 90 resources. And if you are all threads, then I could let 90 threads into the critical section that is the classroom because there are 90 resources available for you. So how do I synchronize that? I can do this with a lock. I absolutely can. One of the beautiful things about synchronization is you can pretty much use each of those primitives in place of the others. But it's just, is it easy to implement it? Is it easy to think about it that way? So a semaphore is a synchronization primitive that is used to keep track of how many resources are available. So in the case of this room, MC 2038, the number of resources available are 90 seats. So we've got 90 seats available, which means I can let 90 threads into the room. So what would happen is when a thread enters, it tries to acquire a seat. If the count of available seats is greater than 0, then the thread can enter and can sit down. And when you are done with your seat, you get up and you increment the number of resources. So when we take a resource, we decrement a counter. And when we leave, we are going to increment the number of resources available. What happens if you arrive at the room and there are no resources available? So the resource count is 0. Well, then you're going to have to sleep. Sleep sitting there at the door waiting. Okay, when's somebody going to get up to go to the washroom? I'll come in and steal their seat. And when a person gets out of their seat and they release the resource, it's their responsibility to wake a thread that is waiting for a resource so that they can come in and try to get it. So we have an acquire and release with the semaphore, but instead of having just one thing available, we might actually have many things available. However, what's really interesting is the fact that semaphores don't use the functions acquire and release. So, to acquire a semaphore, we P the semaphore. And the names of these functions come from the gentleman who created this by the name of Dijkstra. He used the word passering, which I apologize, I don't speak the language, so I don't really know if I'm pronouncing it properly. But it's supposed to mean pass or take. And V, okay, that's when I'm not even going to try to pronounce. It's like VRJIGAVE. And that is how that is the word apparently for release. It's supposed to, and the reason why they are these two words here from Dutch is because Dijkstra, who invented the semaphore, wrote the paper. He was Dutch, and he really liked railroads, and so he named the acquire and release function after railroad signals. So P is for acquire and V is for release. So when we talk about semaphores, we don't usually talk about acquiring and releasing them. We say we P and V the semaphore, and it's really bizarre. Now, if you look at a lot of libraries, they have changed the names to be something a little bit more readable, because if Dijkstra was taking CS135 or 136, he would have lost all his style marks. But in OS 161, semaphores acquire and release is P and V, so get used to seeing P's and V's all over the place. So what can you do with this semaphore? That's actually a really interesting question. So with a semaphore is going to have a wait channel. And a semaphore, instead of having a variable to indicate whether it's owned or not, it's going to have a count of available resources. And when you create a semaphore, you will actually set the initial resource count. Another interesting thing about semaphores is they don't keep track of ownership, because multiple threads could own them. Okay. So we're not actually going to keep track of ownership. When you create a semaphore, you set the initial count. And because you don't keep track of ownership, what's really interesting is you can actually V the semaphore before you P it. And when you're thinking about a lock, that doesn't make sense. You can't release a lock before you've acquired it. But a semaphore is about resources. You can start with no resources and have a thread start to produce those resources. That makes perfect sense. If a baker shows up to their bakery in the morning, presumably their shelves are empty. They have no cupcakes. And then presumably they're going to go into the kitchen and they're going to start baking cupcakes and producing those resources. So their semaphore count started at 0, and then as they bake the cupcakes, they start V'ing their semaphore. So some interesting things. Now, how you initialize and use the semaphore can give it a special name. So the first one is a binary semaphore. So a binary semaphore is a semaphore that has just one resource. So when you create it with resources equal to 1. And then when you use it like a lock. So we could actually take that code from before, where we have that shared variable total, and we can use a semaphore instead of a lock. So I create a semaphore with one initial resource, and then when I want to acquire the critical section, I'm going to P the semaphore. And when I want to release hold on the critical section, I V it. And as long as I treat the semaphore exactly like this, the binary semaphore behaves like a lock. Now, is it equivalent to a lock? No, it is not equivalent to a lock, unfortunately. And the reason for that is there's no protections of ownership. So anybody could release it. And also there's no protections on the counter saying this is the maximum count value and nobody is allowed to produce more things. That doesn't exist. I'm sure there's semaphore implementations that do that, but the generic, the base implementation, no. There's no concept of a maximum count or maximum resources. So it's not equivalent to a lock, because the lock offers us more protection, but so long as you use it properly, a binary semaphore can operate in the place of a lock. And what you're actually going to see later in the course is when we talk about devices and device drivers, we actually use binary semaphores instead of locks, because the lock or the thread that acquired the resource is almost never the thread that's going to release the device. So the only way we can offer exclusion on the device is to use a synchronization primitive that doesn't keep track of ownership, and a binary semaphore is one. Then we have a counting semaphore. This is a semaphore that just has an arbitrary number of resources. So it could start with 0, it could start with 100, it could go up, it could go down. One thing I want to say is semaphore counters don't go negative. Then we have something called a barrier semaphore. Now, again, these are not different implementations. These are different uses. I'd like to show you the use of a barrier semaphore here. So I'm actually going to go over to code. Pretty sure you don't want this directory here. We are going to go, I might as well just use this one here. So this is thread test 1. And you can see here in run threads that after we have this loop that forks off all the new threads, we have a second loop that P's a semaphore once for each thread we created. And that's that semaphore, by the way, starts actually out with a count of 0. And then loud thread, you'll see, V's the semaphore as it finishes. What's going on here? Well, what's going on here is we want run threads to wait for all of the threads it forked to finish before run threads returns. So we have a semaphore that starts with 0 as its initial resource. That means 0 threads completed. We P the semaphore once for each thread we created. In this case, it's going to be 8. Which means I have to wait for 8 V's before this thread here can return. So it's acting as a barrier. We're using the semaphore to create a barrier such that this thread cannot continue until all of the other threads have finished. So for those of you who are like, but P threads join, why doesn't OS 1.6.1 have join? Well, you don't need it because you can use semaphores to simulate that behavior. It's kind of neat, right? And in fact, you can use a lock to do this. You can use locks and CVs to do this. There's lots of different ways that you can simulate barriers. All right, so that's a barrier semaphore. Now, just looking at the time here and trying to decide if I want to talk about producers and consumers. But given that it's like 10:38, I think I'd like to actually finish today early. Normally today would be taken up by discussing how do you test assignment 1, the traffic problem, but since we don't do the traffic problem anymore, we don't actually have to discuss that. So just a couple hints I will give you for assignment 1, testing. So assignment 1, you are expected to write multi-threaded code. There are 2 problems. They're different, but we expect that you're going to use locks and condition variables inside of P threads to actually protect your critical sections. You are not being asked to implement those primitives. You'll do that on the next assignment. But what I wanted to say was that when you are running tests for assignment 1, you might be like, I'll run it 1 or 2 times and then I'm done. No, that's not going to work. Your results are going to depend on how well you've actually implemented the code. Have you done the actual correct solution? And there's no way I can prove to you that you have the right answer. So what you need to do is actually be statistically confident that your code works. So my recommendation to you is to run the code like 1,000,000 times. Okay, not 1,000,000 times. Run it at least 100 times. And make sure that in those 100 times, it works all 100 times. And if you can do that and get no errors, then your code probably works. Now for assignment 1, question 1, where you are asked to find how many times a certain word occurs in a library of articles, we have given you kind of a test harness that creates a random library. You can create your own test harness that has a non-random library. That way you can test your code to validate the fact that each time you run it, you get the correct number of word counts. And we recommend that you do this. The only reason why we gave you the random one is to just give you an example of how to create this. Our TAs are going to be using a different function, one that actually has a fixed count for that. So don't worry about the random. What if the word never occurs? How will we know that it's right? No, we will. We've given you that as a sample driver for your code, and you can write your own sample test drivers, right? And then for the second one as well, we'll be trying with different parameters, and we will be running multiple times to make sure that your code actually does produce the right answer every time. So do make sure that you are executing your code multiple times. I even recommend that you write a script for yourself to actually, automate the running of your code 100 times and have that all dumped to a file, and then maybe write another script to go through and see if you had any error messages or deadlocks. Okay. So that's all the fun things I can think about for talking about assignment 1. Oh, one thing I should mention is that we call locks, but a lot of other people actually call them mutexes. And I think pthreads is one of those that calls them mutexes. So if you're looking through the documentation, and I know I actually put the name of it in the assignment, but you'll actually see they call them mutex. That's what you're looking for. So I hope you have fun with assignment 1. And in our next episode, we will discuss the producer's consumer's problem. And after that, we will look at condition variables and see where we go from there. Maybe we'll talk about some of the other sources of race conditions. So we will see you on Thursday.
Still no sight of them. I don't know what they're doing, but they only got 2 minutes left.